Assalamu alaikum. Today we are going to discuss alternative approaches to observer design. The last class was basically observer design based on the observer canonical form. So if the system is not represented in observer canonical form, then how to deal with it? So either we have to keep the existing system as it is and matching the coefficients, or we can convert our system to the observer canonical form, then designing and then getting back to the original system. So the approaches are similar to the approaches that we have used in case of the controller design. So start with the second one that needs more formulation. So basically a system that is not represented in observer canonical form, z dot equal to az plus bu. And our output is y equal to cz. And our observability matrix for z representation is ymz is c ca ca square and goes up to ca n minus 1. Now if we have our transformation matrix p, that is z equal to px, and we plug this value into this equation, then px dot equal to a px plus bu, and that will give us x dot equal to, if we take p inverse a px plus p inverse bu. So we are interested about C matrix and the A matrix. So the new C matrix, if we plug the values z equal to px into y, then y equal to cpx. So we have a matrix of this system, and also we have the C matrix. So OMZ will be C, which is basically CP, and C, that is CP with A, that is P inverse AP. So you can see P inverse is getting cancelled out. So CP, P inverse AP, P inverse AP. And similarly, it goes up to CP, P inverse AP, and finally n minus n number of P inverse AP. So if you observe carefully, then you can see that the P, these two getting cancelled out, these two getting cancelled out, these cancel out. So basically it is remaining C, P, then C, A, P, then C, A square P, and goes up to C, A to the power n minus 1 P. So we can take common of the P. So eventually it is becoming C, CA, CA square, C up to C A to the power n minus 1. With that we have P. So this is nothing but our original observability matrix OMZ. So this is OMZP. So we can one thing we have to rectify is actually this is X system, so this has to be X. So OMX is equal to basically OMZP. So if you take inverse of OMZ, then you're going to get P equal to OMZ inverse OMX. So one of our objectives is to figure out the transformation matrix, which will be later on used after designing our the gains, feedback gains L. So now the new system that we have, we are dealing with the new system, and so our new error that we have will be, now next step is designing is designing the LX. X is for, because it is for the system X, which is observer canonical form. So the error, we have to choose EX dot equal to, the originally what we have is A minus LC of your EX. So since the system is changed, so what we are going to do here is, so basically we can say that this is for AP of canonical form, observer canonical form, and this is also for X type of system. So you can give X here, and C is also for observer canonical form. So bottom line is the new A's and P's. So P inverse AP minus LX CP. The new P is actually CP, so EX. So this is our error of the state. We can easily link with the previously discussed one. And the output, the error of the output y minus y hat is basically, previously it was CEX, but now it has to be new C, that is CPEX. So since we can write that X equal to P inverse Z, similarly, we can also write that X hat can also be related with the same matrix with P inverse Z hat. So our error EX, which is X minus X hat, should be equal to P inverse Z minus Z hat. So basically P inverse error of Z. Okay, so this is the relationship that we get from the transformation matrix. Now, if we use this into the original matrix that we have derived, EX dot, so EX dot from here, we are going to get, since we are going to go back to the original system, so EX dot can be replaced by P inverse EZ dot, which will be P inverse AP minus LX CP. Then you have also EX will be replaced by P inverse EZ. So P inverse EZ. So, and this side, we converted, this side, we converted using the same idea. So if the error in the state can be related, so the rate of change of error can also be related with a similar idea. So now if you can see that now we can take P inverse into the other side. So EZ dot will be P inverse AP, and also this one will be also multiplied. So P inverse minus P inverse CP, P inverse EZ can be common. So now we can see that EZ is basically A, and these are cancelling each other. So A minus, this will be P. So P LX, or so we just, the LX should also be here. So somehow accidentally was missed. So P LX, and this P and P inverse is going to vanish. Then you have also the C matrix. Okay, so with EZ. So now what we can relate here previously, and what we know that the relationship has to be something like this. Z dot has to be A minus L Z C E Z. So from this one, we can relate that this will be your LZ. So LZ has to be equal to PLX. So once we have designed in the observer canonical form LX, and we know the P, then we can easily find out what will be the value of the gains in the original system, and that will be LZ. And also your output Y minus Y hat can be related as CP. It was now P inverse Z. So CPX it was. So X is replaced by P inverse Z. So this two are vanishing. So ultimately it will be our it was EZ. Okay. So in the original equation it was CPEX. So EX is replaced by P inverse EZ. So ultimately it will give us CEZ. Okay, so this is how we have to go back to the original system. Now with the method that we have explained here, we have to explore into the example 12.8. So example 12.8. So a system is given with G of S equal to 1 by S plus 1, S plus 2, and S plus 5. And this is represented, as they have said, in cascade form. So you have to find out the closed loop performance of the observer is this. And also it is related to your example 12.5 as they have given. And from that one, they already have the equation with which we have to compare it. So that equation is also given, but in the example it may not be given. You have to figure it out based on the values of your percentage overshoot and settling time. So you just figure it out if it is not given, but if it is given directly like this example here, then you just compare with this one. So for the ease of the simplicity, for the ease of the illustration, they haven't gone into the figuring out this characteristic equation, so it is given directly. But in an example, you may have to derive it. So keep the thing in mind. So the first thing that you should do is figuring out the signal flow graph. So basically we have three integrator. So 1 by S, 1 by S, 1 by S. And feedback is -1, -2, -3. They are connected with the gain 1. What is our output? Output is simply in the first value. So with the gain 1, we are going to get the output Y. Is it okay? So, and what about input? So input will be also U, and with the value 1, we have it. So based on this one, we can find out the original system in the cascade form. Z dot equal to AZ plus BU, and that is A is X. This is our X dot. This is our X1 dot. This is your x2 dot, and this is your x3 dot. But since in the Z system, it's actually better to write with the correct notation, even though we are more familiar with X, but it has to be Z1 dot, Z2 dot, and Z3 dot. So as you can see, there is a feedback of -5 as well here. So x1 dot is basically -5 x1 z1 -5 z1, and then you have 1 coming from the z2. So -5 1 0. Then z2 dot is having a feedback from -2 z2, and then also coming from z3. Z3 is only having their own feedback, and so the other values will be 0. So this is our Z plus B. So B is basically only the input is coming to the state 3. So 0, 0, 1, U. And what about output? Output to Y equal to C Z, that is 1, 0, 0, Z. Okay, so original system is figured out. Now we also have to deal with the error of the states. We have to have a replica of the system. So the replica of the system, which is the observer. So same system. Okay, so this time your output is Y hat. And your states will be correspondingly Z1 hat, Z2 hat. So this is how it should look like. Okay, then output. So we should have subtract the input, the actual from the actual output. We have to subtract our Y hat. So now with -1, you can take -1 subtracting with the original one. So original one is coming here with again 1. Then this is actually your Y minus Y hat. So Y minus Y hat will be fed back to the states, rate of the change of the state. So basically this is Z1 hat dot, this is Z2 hat dot, and this is Z3 hat dot. So to the rate of change, we will have the difference. So this will be our L1. Okay. This will be our L2. And this will be our L3. So our objective is to find these values. So you can also say LZ, L1Z, L2Z, L3Z, because it is representing the Z domain. So basically, so since we have our signal flow graph, as well as careful about the signs here, we can also feed our original input here. So this is the complete picture of the observer design with just gain. So you can find out the observability matrix, OMZ, first thing to do, because if the magnitude of this is 0, then our system is not observable. So we cannot go for the designing. So in this case, it will be C, CA, and CA square. We already have shown how to figure it out. So with these, so we are just writing quickly what will be the values. And if you find out the determinant of this matrix, which will be 1, and that is why the rank of the matrix is 3, which is same as the order of system. Okay. So the system is observable. So now, as the system is observable, we can proceed with the next design. And based on this, the characteristic equation, we can easily find out this. Based on the system matrix A, we can find out the characteristic equation of the system. So basically, characteristic equation of the system, which will be actually same in whatever the system we try to represent, will be basically determinant of Si minus A, and which will give us in this particular case S cube plus 8S square plus 17S plus 10 equal to 0. And we can easily represent it in the observer canonical form, which is a companion matrix, which has a companion A matrix or system matrix. So X dot equal to AXX plus BXU equal to basically coefficients -8, -17, -10, then you have 1, 0, 0, 1, 0, 0. This is your X and plus BU. So B is not that important in our case. What we are interested about is the A matrix and the C matrix. So C matrix can be figured out as Cx. The observer canonical form, only the output is related to the first phase variable. So from that knowledge, you can write this to be 1, 0, 0. So now from this one, your OMX is basically Cx, then you have Cxax, then you have Cxax square. And from this one, you can easily write 1, 0, 0 minus 8, 1, 0, 47 minus 8, 1. So we have two observability matrix, which is obtained. And now based on these two, we should be easily figuring out what will be our P matrix that will be used for our representation to convert it to the gain values back to the original system gains. So now once we have the system represented in the canonical form, which is this case, okay, now we can easily go for the designing in the canonical form. So in the canonical form, the designing is basically figuring out AX minus LXCX. So we already know what is AX. LX is the gain that we have to add within in the each of the phase, each of the phase variable. So basically we can write in this way. A is minus 8, 1, 0, then minus 17, 0, 1, minus 10, 0, 0, minus L1, L2, L3. You can also add X if you want. So then you'll have 1, 0, 0. So this will give us minus 8, minus 17, minus 10, 1, 0, 0, 1, 0, 0. We can write directly as well, or we can make it more detailed if you want. But once you're practiced well, you can write it directly, so you don't have to follow the exact steps. Okay, so what we'll have is finally is minus 8 plus L1, then 1, 0, minus 17 plus L2, 0, 1 minus 10 plus L3, 0, 0. Now our characteristic polynomial, if you want, you can go for the determinant. So determinant of your SI minus AX minus LX CX. Okay, so you can go for this one. This is one way, or directly, since you know how to represent the characteristic equation just by looking at the left companion matrix. So the characteristic polynomial has been represented in the left side. So we can write in this way: S cube plus H plus L1 S square plus 17 plus L2 plus S plus 10 plus L3. So this will be our characteristic polynomial. And from the previous example, I think from 12.5, we have the desired characteristics, which is required for 10 times faster observer, and that is actually S cube plus 120 S square plus 2500S plus 50,000. So now we have to compare these two equation, and based on these two comparison, we can easily find out that our LX will be simply 120 minus 8, that is 112, then 2500 minus 17, that is 2483, and 9990. So LX value is calculated. What is next is we have to convert it back to the LZ. Okay, so to convert it back to the LZ, we need the P matrix, and the P matrix can be obtained from the two matrix of observability matrix that we already have figured out, OMZ inverse and OMX. So using the calculator, this is the value you are going to get: 100 minus 3, 10, 1 minus 1, 1. So next is very simple. Your LZ is basically P times your LX. Okay, so P is already figured out. 1, 0, 0 minus 3, 1, 0, 1 minus 1, 1. And then you just multiply with 1, 1, 2, 2, 4, 8, 3, and 4, 9, 9, 9, 0. So multiply. So they will give you the value of the LZ, that is 112, 2149, and 47619. Okay, so once you have these values, what you can do now is you can go to the signal flow graph, and you can replace these values with 1, 1, 12, and this value will be 2147, and this value will be 47619. Okay, so the designing is done. So if you want using the any programming language, MATLAB, control system toolbox in the MATLAB, or using the Python, the Scilab, you can simulate and see how the response can be more faster, 10 times faster compared to the uncompensated one, which is simply without the feedback if you have the observer design. So this is all for this particular session, and this is how you have to design a system that is not represented in observer canonical form. Okay. Assalamu alaikum wa rahmatullah.